to thank the selection committee to have, award me the Akaike Memorial Lecture Award. It's really a great honor. Obviously, Akaike was an intellectual giant. I'm not claiming that I'm remotely at the same level, but still, actually, it's a really, really very great honor to be awarded this prize. Also, I have a lonely story with Japan. I spent a lot of time in Japan, so it's very significant for me, actually. Really, it means a lot to me. So, as mentioned during the introduction, I've been working during my career a lot on these particle methods, on Bayesian computation, on two of my collaborators sitting in the audience, including Christophe, who was the collaborator on the particle MCMC paper. But over the past few years, I've changed a little bit of a research direction. So for about maybe 10 years, I decided that maybe the way to scale Bayesian computation was to use ideas from optimal transport, for measured transport. And I started working on that in 2012. To be honest, not quite successfully at the time because we were missing the tools. But this is an idea that I've kept revisiting over the years. On essentially what I'm going to talk about is about the work we did in these directions over the past now 5-6 years. Okay. So the title of the lecture might appear a little bit obscure to start with. The Schrödinger bridge. I will explain obviously what it is. Computation and application. On a subtitle to the talk should be like really measure transport for generative modeling on essentially Bayesian computation. Okay, so this is really work done with many collaborators that I will list at the end of this talk, but I will basically, in particular, mention Valentin de Bordely, who has been instrumental on key collaborators on pretty much all this topic, all this project. Okay, so this line of research essentially has been motivated, actually guided by the introduction of a novel class of generative modeling techniques in machine learning. Okay, so that's the basis of the work I'm going to present here. So I'm going to start basically by starting this lecture by reviewing some of the work in machine learning to do generative modeling that has become very popular nowadays. And I will see essentially how we can extend this type of ideas to a more general setup so as to solve the Schrödinger bridge problem, which is somehow some kind of entropy regularized version of optimal transport. And then later I will discuss some application to Bayesian computation. Okay. So what is generative modeling? This is actually a very key research area in machine learning, which is at the core of all this generative AI revolution you've heard of, I'm sure, if you're following any tech news, actually. Okay, so really the problem can be formulated as follows. So this is a very loose formulation of the problem, but essentially this is the way it's stated. So it's suppose that you have access to n samples from some distribution. Typically, I'm going to take an image as an example that this sample corresponds to, say, an image. Okay, so you have access to n images. So they're coming from some distribution, a distribution pi of the image you have that are available to you. And really what you're interested in is to generate new samples, that is new image in this case, which are approximately distributed from the same distribution. But you want obviously this new sample not to be some kind of carbon copy of the one that you have in your database. You want something that can generate some kind of diversity. And you want them at the same time to be fairly similar to the one you have in the database, okay? So that's really the idea. So you have n sample for some distribution. It could be images, music samples, proteins, and you want from the distribution pi, and you want to generate new sample from this distribution, okay? So why is it interesting? Well, it turns out that this thing could be interesting because, for example, in a kind of data-rich environment, we are now, we're facing a deluge of data. You could use this kind of techniques so as to kind of, design some kind of data-driven prior distribution if you, for example, Bayesian. Okay, so that's something I could do. Say, for example, you're interested to design to solve an inverse problem for some kind of natural images. You'd like to put a prior on the distribution of natural images instead of using a Markov random field like people used to do in the past, which do not correspond really to sample of natural images. You could use a generative model instead, okay? Which would provide a much cleverer, much better, essentially prior distribution. So that's one type of application. The other thing why people are interested in this is that, for example, there you might be interested in training some kind of self-driving car. So you have a vision system, and to train this vision system, you need to feed to the kind of the vision system like hours on hours of actually data, which are very expensive to collect. So what about being able to synthesize those data so as basically to train your vision system? So that's one other type of application people are interested in. Okay. So there's a lot of work on that. For example, my colleague at DeepMind have worked recently on application of this generative modeling for weather forecast, where they've obtained actually state-of-the-art result. And that's been deployed. Some of these results have been deployed by the Met Office in the UK. Okay, so because it's so important in machine learning, there's been like a plethora of methods that have been developed over the past, literally, say 15, 20 years. So I'm not going to review all of them, but I just mention some of them. I'm sure some of them you're familiar with. There's this concept of energy-based model, where essentially you try to parameterize the distribution of your data by some kind of, Gibbs distribution, and you try to learn the potential of Gibbs distribution by maximum likelihood. You could use this kind of normalizing flow, which is also related to the idea of transport, where you have some kind of simple base measure that you're going to transform by some kind of sequence of diffeomorphisms so as to obtain, a distribution that capture the data distribution, variational encoder, and one type of technique that was very, very popular till, the past, until 2020 is generative adversarial network. So that's a kind of algorithm, that class of techniques for generative modeling that, has been, proved invaluable in the past. But it turns out that all these kind of techniques that were very, very popular until, essentially 2020 just got superseded by something which is basically known as denoising diffusion model. Okay, so really, I'm going to talk about this class of techniques because this is the basis of what basically I'm going to build on this class of models to kind of really develop a way so as to solve Schrödinger bridge problem. Okay, so what is the denoising diffusion model? So just basically a generative modeling technique. Well, as I told you, it's kind of quite popular. So there was the first paper in 2015 that was basically published. By the time, people didn't pick it up. It was not something that people picked up really right away because there were some elements missing on the experimental result were not very convincing. But it was revisited by two groups of researchers in Berkeley and in Stanford. And they proposed actually some kind of elaborated on those ideas to come up with a class of powerful generative models. And we see that basically those methods became in a few years extremely popular. You see some of the papers I've already published in 2020 have already 10,000 citations. Okay. So why is it that people have used those techniques, using those techniques a lot? Well, just because it provides actually remarkable empirical results. Okay, so if you look at the, generation of synthetic images, really, there's a lot of systems which are currently available. ImageGen from Google. There are people like, there's Midjourney, sorry. There's stable diffusion, and all these techniques to generate images are based on this idea of diffusion. But not only that, you can basically, it's been used to generate 3D scenes now. More recently, there's been also efforts so as to generate videos. Okay, so you just basically able to generate complete video, synthetic video, using this type of ideas. So, for example, there's been obviously Sora by OpenAI and also Veo by Google. Okay, so similarly, more application to audio have been on music have been proposed. Those techniques work remarkably well, and there's actually a lot of applications that are already available. So, in particular, if you try to do if you have a Pixel phone, then you can see that the recent generation of Pixel phone for image, improvement or essentially image in painting is all based on this type of approach. Okay. But not only, if you're not interested in media application, which is fair enough, you're more interested in kind of like science application, then those techniques have also been applied successfully to the generation of protein, actually. So people have been able to synthesize new protein basically on the computer. On this protein, basically people have been able to actually produce them in a lab, actually. So that's actually really kind of big business at the moment. Okay, so what are diffusion models? So don't want to spend all my lecture on diffusion models. I will do a kind of very kind of brief introduction to them, just to get you an idea, a gist of what's going on. Just to introduce diffusion models are going to be based on diffusion process, obviously. So I'm sure most of you have a background, where they've studied diffusion process, but in case you haven't, I have one single slide of introduction, okay? So this is a stochastic analysis or stochastic calculus in one slide, okay? So basically, what's a Brownian motion? A Brownian motion is a continuous time stochastic process which has essentially independent Gaussian increment. Okay, so if I give you basically the process at time t plus delta, that's going to be bt equal to bt plus some Gaussian random variable of standard deviation root delta. Okay, so that's basically the key process essentially to define stochastic differential equation. The stochastic process that is really behave like some kind of erratic, motion, the Brownian motion, and it was introduced in physics to describe the evolution of particles. Essentially, what we're doing a stochastic differential equation, which is going to be the key of what we're going to describe later on, is that we pick a process. It looks like an ODE, okay? So you have a drift btxt, but then you add also some kind of stochastic perturbation, which are essentially driven by a Brownian motion. So if you're not familiar with all this continuous time process, it kind of doesn't matter. Think of it as a discretized version of this process, and what you obtain is a simple, essentially non-linear autoregressive process. Okay, so that's kind of really rough background for that people are using when they define this type of model. Okay, so what's the idea? How do people exploit this idea so as to do generative modeling? Okay. So the idea is as follows. So you have data that are available to you. Okay? You have data available to you. What you're going to do, you're going to basically take the data which are available to you, and you're going to noise them progressively, essentially by using a diffusion process. So essentially, you start from a data point, say, you apply a stochastic differential equation, which is a kind of Einstein-Beck, and it progressively destroys the information and the data, so that essentially you obtain, after a time long enough, essentially a Gaussian noise sample. Okay, so you go from the data distribution to a Gaussian distribution by just running this kind of stochastic differential equation, which is a simple Einstein-Beck process. This is the time discretization of a Gaussian AR process. Okay, that's the simple idea. So you have a very simple way to go from the data distribution to the Gaussian distribution by just running forward this diffusion process. Now, what I'm telling you, if you want to generate data, the only thing you need to do is basically to do the reverse. So basically, you're going to start from the endpoint. And your endpoint is roughly distributed according to a Gaussian distribution. And you're going to simulate the time reversal of the noising diffusion. Okay, so you're going to do that. On the right, this is the expression of a time reversal of the forward diffusion I've written before. And if you run this time reverse diffusion, then you're going to get at that time 0. This basically, you're going to have a sample from the data distribution. So really, diffusion process, this idea is really you have a forward process that takes you from that transport the data distribution to the noise distribution. And essentially, you simulate the time reversal of this operation that takes you from the noise distribution, a Gaussian, to the data distribution. Okay, so practically, to simulate exactly this time reversal is complicated. That's involved, in particular, computing what we call the score, which is the gradient of the log density of the marginal distribution of xt under the forward diffusion. But you can approximate this kind of this kind of quantity using score matching. And score matching, is actually a class of method that was developed by Ivarinen, who was the recipient of the Akaike Memorial Lecture Award 2 years ago. So there's ways to do that. Okay, so but the key at the high level, the thing you need to have in mind is that this really denoising diffusion model is just basically learn a transport between, data distribution to noise distribution and vice versa. Okay, so this is kind of measure transport you're doing when you're implementing this type of algorithm. Right? This is an application to some kind of protein design where you start from Gaussian distribution, and roughly speaking, eventually you cool down, basically go back to have a sample from the data distribution. Okay, so that's nice. That's a very neat idea. It has proven extremely popular because the empirical results are actually quite impressive. Because basically this has proven so impressive, people have said, oh, could we extend this? Is there any way we could extend this concept? So now we have just a way to transport from the distribution of data to the distribution of the noise and vice versa. Okay, but could we define transport using this type of ideas between distribution that are basically, arbitrary, two arbitrary distributions that are on the same space? I don't know what happened. It seems that my connection internet has cut. Do you see anything? It's okay still? I don't know what's going on. I had no problem. New Wi-Fi. Okay. It's going to work again. Yes. It work? Okay. It seems to work again. Okay. So people thought, let's try to extend those techniques to more general concept. Oh. Yes. It's okay. Okay. So there are two setups. It turns out, yes, those techniques can be extended. And I'm going to distinguish two settings. So there's the settings where basically, which we call essentially the pair setting. So where, say, you have a couple, you have access to data, which correspond to an image on the corrupted version of the image. So assume this is the data you have access to. Okay, so this is essentially a joint distribution between, you have access to the joint distribution of image on corrupted image. Okay, some sample from that. On using this kind of technique, what you're able to do is to come up with approximation of the conditional distribution, say, of the corrupted, the clean image given the corrupted image. Okay, this is something you could do using this kind of techniques. One way you could do, so for example, that's called data translation. Think of it also for text. It would be you have access to a collection of text where you have the Japanese version and the English version, the translated version. Okay? And really what you do with this type of idea, you learn essentially either to basically sample from the Japanese translation given the English text, or basically you try to sample from the reverse, you try to sample from basically the English version given the Japanese text. Okay, so that's actually quite remarkable that you can do this using also these techniques. So that's one text. It's used quite a bit in machine learning for this actually domain transfer learning. Okay? So this is a case where you have really access to sample from essentially a joint distribution between, say, as I say, image on clean image on noisy image. Okay. But what about the kind of like more challenging problem, which is the scenario where you want to do some kind of transport map and you don't have access to pair data, you only have access actually to unpaired data. So for example, you have access to a collection of low resolution images on a collection of high resolution images, actually. But there's no pair. You've never been given actually joint sample from low and high resolution. Okay? And what you want to do is based only on this kind of data, you want to be able to essentially sample from actually the distribution of a clean image of a high resolution image given low resolution. So this is kind of problem you might be interested in. So we have an application in climate science where this type of problem are actually quite common. So they have access to really a few high resolution images, a lot of low resolution image, and essentially they want to be able to learn some kind of transport map so that essentially next time when they're given a low resolution image, they can actually infer a high resolution image. Actually. So this is this kind of what unpaired data. And in the context of text, again, it will be the scenario where you're given a collection, of, say, of Japanese text, a collection of English text, or there's no pair. Okay, so they're unrelated. And you want to find a mapping based only on those data. You would like to be able to still come up with some kind of translation. Okay, so we are interested in doing this. So this is just a summary of basically this type of ideas. So what people have done so far, you have like, you want to do generative modeling, so you come up with this kind of diffusion model idea to go from Gaussian to data, data to Gaussian. So data to Gaussian is trivial, Gaussian to data, you have to learn this time reversal, but you can do it using score matching. Then people realize, well, now can we extend this thing to this kind of pair data where you given sample from a joint distribution, so clean image, corrupted image, and try to learn a mapping that gave you some, say, corrupted image to clean image? Yes, you can do that. This is the pair setting. And what about the unpair setting, where basically you're given, like, say, a collection of clean image and a collection of corrupted image, and they are unrelated. You never access to have pair to pairs of data, and you try to learn a mapping that takes you from one distribution to the other. Okay, so this is the unpaired case. So this is what we're gonna look at is this basically this setting. So in the machine learning, people call that unpaired data translation. Okay. So there are various ways to do this. But to define it mathematically, we're going to rely on the kind of notion of so-called optimal transport. Okay. And then we'll see that solving the optimal transport turns out to be fairly complex. So instead, we're going to actually rely on some kind of regularized version of optimal transport, which is easier to address. Okay, so what is the optimal transport? So remember what the problem I have. I have basically sample from two distributions. I'm going to call pi naught pi 1. And essentially, I'd like to trying to find a mapping that will basically is able to essentially going from pi naught is able to provide sample from pi 1 or vice versa. Okay. So what I'm going to interested in solving is the following problem. I'm going to say, okay, I'm going to look at all the set of all joint distribution with marginal pi naught on pi 1, okay, which minimize this expected cost. And for the rest of this talk, this expected cost is basically the square Euclidean distance. Okay? So that's what I want to do. So I want to find essentially the joint distribution, which has the right marginal pi naught pi 1, but I want it essentially this joint distribution, so there's infinite number of distribution that have those two marginals, but I want to find the one among all those that minimize this cost, this expected cost. So I want to minimize the distance essentially between the sample of the joint distribution. So there's this extremely well established theory for optimal transport. But the problem is that even we have discrete distribution here, it's kind of actually very expensive to compute. So you have n sample from pi naught, n sample from pi 1. The cost to compute is n cubed. Okay? Using the Hungarian algorithms. I think the algorithm is a bit faster, but it's still very expensive because in the application we're thinking of, the number of data sample I can have can be, 1 billion, literally. So that's not scalable. So that's not quite good. Okay, but this is what we like to do. We like to be able to still solve this problem. What we're going to use is a kind of trick that is fairly standard in machine learning, which is basically going to add actually entropic regularization. Okay. So we're going to say, well, instead of solving this problem that you've given me, so you have sample from pi naught, sample from pi 1, you want to find the optimal transport. I said this is too expensive, the existing algorithm. Well, what we're going to add some kind of entropic regularization here. Okay. On this entropic regularization, essentially, it makes the problem, it's going to make our problem actually much simpler. Okay. So first, what we find is that the transport you compute by using this type of ideas actually has better properties, essentially, in particular, is more robust to perturbation of pi naught on pi 1, which is a very desirable effect. Okay. So what you could do is that if you had access to, if you have access to just sample from pi naught on pi 1, you can actually solve it using an algorithm which is known as Singh algorithm. So this is something that has been, introduced in the machine learning by my colleague, Marco Cuturi, who spent a lot of time in Japan. So that's one thing you could say. You could say, oh, that's not a problem. Just basically you have your n sample from pi naught pi 1, and just basically use the Singh algorithm, and it's going to solve the problem. Well, the problem is that doesn't work for our problem because we have far too many data. And the Singh algorithm has cost n squared, so that I cannot run that on my computer. Even at Google, we cannot do that. It's too expensive. So we need to come up with also a solution that bypass the use of these techniques. Okay, so you could use this kind of mini batch OT, but it just introduced actually significant error. So that's not quite good. So what I'm going to do? Well, we say two things. So first, you could say, okay, you spend your first part of the talk, introducing this measure transport with diffusion. But now when I move to this kind of optimal or entropic optimal transport, problem, I'm not talking about any dynamic or diffusion anymore. I'm just talking a static problem where you have a joint distribution with two marginal pi naught on pi 1. So my question is, where are my diffusion? Why did I speak about diffusion to start with? Is basically after half of the talk, I'm not talking about that anymore. Okay, so it's, we want essentially to reintroduce this notion of diffusion within the basically to solve this problem. Also because, empirically, there's a kind of evidence that having this kind of strategy of iterative refinements for diffusion, it actually has substantial empirical benefit. Okay, so what are we going to do? We're going to say, well, actually, it's possible to reformulate the solution of this entropic regularized optimal transport on some basically continuous time stochastic process. So what I'm going to say is that consider the following problem. Okay, so I give you a process Q, which corresponds to a Brownian motion. Okay, a Brownian motion of standard deviation epsilon. Okay, so remember the Brownian motion. The Brownian motion was basically this continuous time stochastic process with independent Gaussian increment. Okay, and now I'm saying I'm going to be interested in essentially identifying process, a diffusion process, which has a path distribution that is the distribution of all the joint variable or all its variable between the interval 0, 1, is closest to the distribution of the Brownian motion in Kullback-Leibler divergence, subject to this process having the marginal pi naught at time 0 and pi 1 at time 1. Okay, so I have transformed the static problem I had, where there was no diffusion involved, into the problem of looking at the stochastic process on the time interval 0, 1, which has actually the right marginal, P naught, P1, and is closest in basically Kullback-Leibler divergence to the Brownian motion. And it turned out that if I can solve this problem, which is known as the Schrödinger bridge problem, then I'm done. And the reason I'm done is because if I look at the solution to this problem, the Schrödinger bridge, then basically the joint distribution of the endpoint of basically the Schrödinger bridge correspond to the solution of the static entropic optimal transport. Okay, so that's actually a remarkable fact. It's actually quite easy to establish it. I'm going to skip that because this would be far too long to explain, but this is actually quite simple to prove. Okay, so here I present an illustration of Schrödinger bridge. I have two distributions, pi naught here in orange and pi 1 in blue. And here, this is an illustration of a diffusion that takes me from pi naught to pi 1. Okay, so this is a realization of the Schrödinger bridge. Okay, so for the timing, I haven't done anything. I've just said, like, literally, I've reformulated saying, oh, there's an entropic optimal transport. Actually, if you want to solve the entropic optimal transport, you can reintroduce kind of continuous time in this setup on the diffusion kind of framework. But I haven't shown you how to solve this problem. Okay, so this is basically what I'm going to do during the rest of this talk. Okay. So first, a bit of history. All this Schrödinger bridge formulation appeared when I was obviously proposed by Schrödinger, hence the name. So it was proposed in a 1931 paper on the reversal of the law of nature, where the problem Schrödinger was interested was the following one. He said, okay, I have a collection of particles at time 0, the distribution of this particle is pi naught. Okay, and then I assume I have some kind of physical knowledge that tells me that really these particles should evolve according to a Brownian motion. Okay, so basically, typically, what you say, well, okay, so what you should observe at pi 1, you should observe pi naught, the measure pi naught that has been transported by this Brownian motion. This is what you should observe. But then he said, well, it was a work based on actually experiments. Well, it turns out that at time 1, what he was observing was not actually pi naught transported by the Brownian motion dynamic. It was a measure that was distinct. He was observing a different measure, which call it pi 1. And he was saying, okay, then what I'm gonna look is what is the most likely, evolution of my particle which are consistent with the observation I've gathered, that is that the particle at time 0 are from pi naught, and the particle at time 1 are pi 1. Okay? So this is how he came up with this formulation. It was completely motivated by the physics, and he has actually some interesting derivation in this paper. So this thing is proposed by physics, but it has actually a long history in also mathematics. So the Schrödinger bridge thing has actually, motivated a lot of theoretical work. So there are many specialists of this kind of probabilists who are specialists of this research. So I take in France Christian Léonard, pure probability guy, who's been really doing quite a lot of work on the kind of theory behind the Schrödinger bridge. And in Japan, you have this Professor Mikami that I've never met, but who has actually done a lot of theoretical work on actually Schrödinger bridge, on extension of it. So this is a kind of like active research area of mathematics, still a lot of paper published on that. But till recently, there was mostly theoretical work, and there were really no scalable computational method to solve the Schrödinger bridge. It was really mostly theoretical work. So really where we come in is like we're not working on the theory of Schrödinger bridge, but we're trying to come up with an algorithm to solve the Schrödinger bridge. Okay. So remember, just before I basically switch to our solution, what I'm interested in the thing, so I have a Q here is going to be a Brownian motion for the sake of this talk. It could be more general. And I'm trying to find a path measure with the distribution like the distribution involved basically induced by a diffusion, which is closest to the distribution of Brownian motion subject to terminal constraint. At time 1, at time 0, its marginal distribution is pi naught. At time 1, it's pi 1. Okay. So we're going to use this following characterization of the Schrödinger bridge. So what do we know about the Schrödinger bridge? Actually, because people have worked a lot on the Schrödinger bridge. So actually a lot of result on it has been characterized in a kind of elegantly. So the Schrödinger bridge is the only path measure which basically admits pi naught as a marginal distribution at time 0, pi 1 as a marginal at time 1, is a Markov, is induced by a Markov process, okay? And is what we call reciprocal. So what does it mean, reciprocal? It means that the conditional distribution of the path given the value at the endpoint is the Brownian bridge. Okay, so that's an important thing. So I know I have access to this information. And among, if I have a path measure basically that satisfies all these 4 conditions, then it's the Schrödinger bridge. Okay. So there are various ways to solve it. So one thing that has been very popular in the literature, and actually was proposed by Forte, it's a French probabilist in the 40s, and he was rediscovered a lot, actually in many literatures, and it's known as iterative proportional fitting in the stats as well, is the following thing, is that what you're going to consider an alternate projection algorithm. So you start with a path measure, okay? Assume it has basically a marginal distribution at time 0 pi naught, and you're going to kind of iterate. So you have your path measure, say you take pi naught, you drive it by the Brownian motion. Well, at time 1, it turned out that you don't have pi 1. So what you do is that you now do an alternate projection where you start from pi 1, okay? And you're going to basically look at the time reversal of the diffusion you had, and you keep iterating between these alternate projections where you enforce that at time 0, the marginal distribution is pi naught, and at time 1 later on, and the next iteration, the marginal distribution is pi 1. And you keep iterating these kind of things, okay? And it turns out this algorithm converges to the Schrödinger bridge. It's a well-known fact. It was actually established rigorously in the 40s. Okay, so algorithmically, how would it look like? I'm going to spare you the equation, but in the context I was interested in, say, assume you are in the scenario where basically you have pi naught is the data distribution, pi 1 you like it to have a noise distribution, you use as a reference dynamic an OU process or Schrödinger process instead of Brownian motion, and your process is such that basically if you take pi naught and you transport it by the Schrödinger, at time 1, it is not is too far from the noise distribution. Okay, so this is an example here. So this is your data distribution. You run your algorithm, basically, you drive it, you use it to drive an on-chain process. And what you observe, basically, at the end of the basically running your on-chain process, well, you observe something that is not a Gaussian distribution. It's not the noise distribution, okay? So what you do in the kind of iterative proportional fitting algorithm was you say, well, okay, what I need to do, I need to iterate the process. So now you say, okay, I'm going to enforce the marginal constraint at time t, at time 1. I want it to be the noise distribution. So I restart from the noise distribution and I time reverse the forward diffusion I was given. And you do it, you obtain a new distribution at time 0 that doesn't correspond to the original data distribution. So you restart from the data distribution, you time reverse the previous diffusion you had, and so on and so forth. And if you do that, you converge towards the Schrödinger bridge. So that's one way to do it. So that's one thing we proposed early on in 2021. Problem is that basically this algorithm, there's some kind of unstable. If you run it too many iterations, there's a kind of accumulation of error. It's not quite stable. And in particular, what you lose is this, numerically, you end up losing these reciprocal properties, which is, remember what is a reciprocal property? It's a thing that tells you that the Schrödinger bridge should be such that conditional upon the endpoint, you have basically the distribution of the remaining variable follows the Brownian bridge. Okay. So what I propose is an alternative algorithm, which we call iterative Markovian fitting. So instead of projecting iteratively on the set of path measure or marginal pi naught at time 0, pi 1 at time 1, what you do, you start with an original measure, okay? Say a reciprocal measure. So you say you have you start from pi naught, pi 1, and you put a Brownian bridge in between. That is a reciprocal measure, okay? And then what you're going to do, well, you're going to say, okay, this is not really a Markovian measure, this measure, because it's just basically pi naught, pi 1 with Brownian bridge between. So what you're going to do a Markovian approximation of it. And you keep iterating between these two projections, alternating between Markov projection and reciprocal projection. On this algorithm, we show converge also to the Schrödinger bridge and has better numerical properties, actually. So how does it work practically? Let's see, it's actually quite simple. So here I start from a measure. I said assume this is here, this is pi naught, sample from pi naught, sample from pi 1 here. And what you do, you build a path measure that is basically reciprocal by simply drawing, actually sampling from pi naught and pi 1 and building a Brownian bridge between those points. Okay, so this is the type of path measure you obtain. Okay, so you do that. On this measure, actually, you can write actually this measure, you can show that this measure is obviously not Markovian measure, okay? And actually, it is defined by this process. So here, this is the distribution of the endpoint, and here, this is just what I've written is just a Brownian bridge, actually. Okay. Now you say, okay, I want to project on the set of Markov measure. So it turns out that the only thing you have to do if you want to project a kind of actually such non-Markov path measure on the set of Markov path measure, basically is to replace x1 here by the conditional of x1, the conditional expectation of x1 given xt. Okay, so you can do that. You can do that by regression. On that, define a new path measure, which has exactly the same marginal as the non-Markovian path measure, but basically now, by construction, we have a Markov measure. So we do that. So this is the way we go from actually non-Markov path measure, a reciprocal process to a Markovian process, and we keep iterating this thing. Okay? So again, here, this is the measure I have. Okay, this is my Markov measure that I have obtained after projecting my non-Markov path measure on the set of Markov measure. And what I do, I want to project it now on the set of reciprocal process. So the only thing I need to do is to delete everything that happens in between, okay? And replace everything now by Brownian bridge. That's it. Okay. So we've applied this type of ideas to actually climate science. So remember, this is a case where I'm interested in, where I have access to low resolution image on high resolution image of supersaturation on vorticity field. Okay. As I say, in this context, there's no kind of paired data set. It just kind of doesn't exist. And it's not like you could take your high resolution image and try to basically get a low resolution version of it, because this is complicated to do that, because the way you obtain low resolution is not just by averaging the pixel value, it's just basically obtained by solving some kind of Navier-Stokes equation. So it's actually much more complicated. Okay. So what we do, we have those two empirical distributions, and we learn a Schrödinger bridge between those two distributions, and that allows us actually later on, once you give me a low resolution image, I infer a high resolution image. Okay, so this is an example here where basically I have kind of low resolution image, and basically this is the kind of high resolution image I obtain. And in terms of, we obviously check how it was performing compared to alternative techniques in terms of like, alignment on a test set, and it was actually indeed out of the box improving over current techniques. Okay, so this is kind of interesting ideas, but it's expensive. That's the real problem of this kind of technique. So really what you have to do, you alternate this kind of projection on the set of Markov measure, projection on the set of reciprocal measure. Projection on the set of reciprocal measure is trivial, but solving like this kind of Markovian projection step, it requires actually estimating some kind of conditional expectation, and this is as expensive as actually training a diffusion model at each iteration. Okay, so that's not quite good. It's not also, from a kind of pure practical point of view, it is not kind of actually compatible with the code base people use to train diffusion model. So they don't really like this algorithm where you have like, you train a diffusion model somehow, you do another iteration, you train another model, and say, no, it's too much, okay. So the question is, would it be possible to come up with a kind of simpler online algorithm so as to shift it? Okay, so this is what we wanted to do, so as to kind of improve the essentially the conventional complexity, and have an algorithm that is more compatible with what people would like to see in their code. Okay, so this idea is based on this kind of Schrödinger bridge flow. Okay, so the idea is, there's a minus sign missing here. I thought I had corrected it, but it doesn't show. So you're going to define a flow of probability measure. So put a minus in front here. There's a mistake. And essentially, you want to, this flow of probability measure, okay, on a path space, as a stationary point, which is essentially the Schrödinger bridge. Okay. And essentially, you want to come out an algorithm so as to implement numerically this flow. So what happens, so the minus is back here. What happens is that when you discretize actually this algorithm, this flow with a kind of step size alpha, you end up with an algorithm which is like that, essentially, okay? So this is everything here at the level of path measure. So we say, well, the path measure I want to compute at iteration n plus 1 is 1 minus alpha, the path measure at iteration n, plus the path measure at iteration n, again, there's a typo here, sorry, which is projected on the Markovian projection on reciprocal projection. Okay? And if I do that, actually, this algorithm, so what do I have? I have the thing that for alpha equal 1, it recovers the algorithm I had before. Okay? Now, if alpha is more general, then this algorithm still converges toward the Schrödinger bridge. So it converges for any alpha between 0 and 1. I have another internet problem, unfortunately. Alors, I don't know what's going on. Too much. Yeah, I try. So a problem with eduram that doesn't work actually. Okay, can you try? of a network. Yes, sure, let's go. So while Kango is sorting out the internet, so remember what we had? We had this literally alternate projection algorithm, which is like you have your path measure, it's a reciprocal measure, then you project it on the space of Markov measure that requires actually learning some kind of conditional expectation. Your regression is quite expensive. It's as expensive as training a diffusion model. Then once you have this kind of Markovian projection, basically you need to sample from it, and then you obtain, again, you define a new coupling between endpoints, you do reciprocal projection, and you iterate. It's kind of really expensive, actually. So that kind of works well, but really it's a bit too expensive. So now what we're trying to do is come up with a kind of online version of that. Okay, so we don't have all this alternate projection thing. We do everything by minimization of a single cost. Is it okay? Yoram is back online, actually. No? Tu le vois? You need to reconnect, no? Yes. Okay, so this is the problem. So we have this nice property that this algorithm converges to the Schrödinger bridge, but so this is an extension of what I had presented before, but it's really unclear how you're going to basically solve this. So turns out, actually, that you can, if you can, by doing some kind of functional gradient descent, then you can actually you can implement this recursion. So I think we're not going to have enough time to go for detail, but the key thing is that I can rewrite the iterates I have defined before, essentially as simply the solution of a functional gradient descent algorithm. Okay, so this is the kind of key of this slide here. And this thing is important because it means that practically we can implement the algorithm by just minimizing essentially a single objective. So that is actually the main result behind all those slides. So I'm just presenting some simple thing. We're gonna skip the detail of the algorithm. It's too complicated, but we can do like this kind of transfer learning between, say, the distribution of some characters on distribution of some digits. And we see that by using this kind of ideas, we are able actually to obtain a better result at the technique that do not rely on optimal transport and at the kind of fraction of the cost of what is basically computational cost of the first the alternate projection method I was discussing before. So we did that also for this kind of transfer learning, when you have some dogs and you're trying to go from dog to cat, or from like a pet to wild animal, and this kind of thing scales actually quite well. So this is more illustration of this type of ideas, where we actually just do transfer between a cat and wild. Okay, so this is cat here, and the wild is what we obtain by just using the transport that we've computed using this kind of Schrödinger bridge, and vice versa, where we transfer from wild to cat. Okay. Okay, now I want to finish because this lecture, I'm not gonna have a chance to do it, but my original motivation, as I discussed, was to say, well, okay, it's good to do generative modeling, but I spent all my life doing Bayesian computation, so could these ideas be used so as to actually solve Bayesian computation problem? It turns out obviously the answer is yes. So really, just making, I'm not going to go in detail for this too much, but anyway, so you assume you have a probabilistic model, which is described by a joint distribution Pxy, okay? where X is the parameter or state you want to infer and Y is the observation. And you can sample as much, you can obtain as many samples as you want from this joint distribution. Okay? I do not need to know anything. I don't need to know the analytic expression. So it can be given by a simulator, a complex simulator. But I assume I can sample from this joint distribution. And really what I want to do is I want to, for a given observation, later I might be collecting, it's called Y-ops. I want to be obtained to sample from the conditional distribution of X given Y-ops. Standard problem in Bayesian computation. All I'm saying is that essentially you can reformulate that as the solution of a Schrödinger bridge problem where you work on an extended space. Okay, so you're not trying to do a Schrödinger bridge between, say, a Gaussian distribution or the posterior distribution of interest. Instead, you compute a Schrödinger bridge onto the joint space of like state on observation, where you have one conditional distribution. Basically, you consider one fixed distribution, consider time zero is the joint distribution of interest, the joint original distribution. Okay, on the terminal one, say at time one, is such that basically you put an easy to sample distribution for the state, and you consider exactly the same marginal distribution of the observation for Y. Okay, so if you solve this problem, the Schrödinger bridge problem, with an adequate actually reference measure Q, which essentially is such that it doesn't modify the observation Y. So you have a process on the observation space which is completely trivial. Then it's easy to show that you can actually sample later on from the conditional distribution of X given Y. Okay, so that's kind of nice. And this is somehow a generalization to do Bayesian inference. It's a kind of ABC type algorithm, actually. Okay, so you can apply that to nonlinear filtering. I just keep it. It's quite expensive. I'm not saying we've solved this kind of, it's a revolutionary approach to solve filtering, but it's an alternative approach that completely bypasses actually using kind of particle methods. Because at no stage you're ever doing important sampling when you're doing that. So in a sense, this is an alternative to this type of approach. It comes, unfortunately, with much less theoretical guarantee for the time being. There's a lot more work to do, but you can be competitive and do actually significantly better than techniques such as ensemble Kalman filter, and actually even in some solution we was doing actually, it was on par with particle filter on low dimensional model, and it can scale to actually higher dimensional model. So this kind of idea are actually quite interesting also to do Bayesian computation. Okay, so I just want to conclude. So this kind of diffusion model ideas, really, that we are introduced to pure generative modeling, they can be extended to solve this unpaired data translation problem. I give you two arbitrary distribution, and essentially I try to find a mapping that takes you from one to another, and you want this mapping to be regular somehow, that satisfies some kind of optimality property. And in our case, we solve actually, essentially, entropy regularized version of optimal transport. So one criticism of this algorithm is that they are not what we call simulation free. So what simulation free in this literature means is that it said that at some stage we need to simulate forward some SD which are non-trivial. Okay, so as to do the learning. So that's actually one of the limitations of this algorithm. So there are algorithms that bypass this problem, like algorithm relying on mini batch optimal transport and synchron. But I say this type of techniques do not scale for the application I have in mind, actually. So for small application where you can do that, it's good. But for the application we're considering, it's actually not scalable. Finally, we have convergence result on saying, for example, the Schrödinger bridge, the kind of recursion we have, converge to the Schrödinger bridge, and so on and so forth. But the existing results we have remain extremely incomplete, like they're very incomplete for diffusion model, in a sense that they do not really explain some of the remarkable empirical performance we capture. So, I mean, there's a lot more work to do to understand the limitation of this type of approach. Actually, we are far from being done here. It's an interesting direction, but much more work to do so as to kind of really understanding mathematically what's going on. I'd like to finish this talk by basically acknowledging my co-authors, actually, who are in Google, Apple, ESSEC, and Oxford. Thank you.
Okay, thank you very much for first for the invitation. So Kengo and the committee who approved me discussing Arnaud's talk. And Arnaud, thank you very much for your very nice presentation and all your work. So before basically more or less reformulating some of the things that Arnaud has said and asking question, I'd like to provide some background. So I've been in Japan for a couple of weeks, and I've realized that there was some kind of parallel between reading the machine learning literature and climbing the Narayama mountain. I mean, that's a repetition. And sometimes when reading the machine learning literature, you feel that you're promised basically enlightenment if you reach the summit of the mount, but you've got to go through many gates, and you can get lost, and you can even miss basically the shrine and get lost. And in addition, sometimes reading the papers. So if you think of the Tories as being the papers to a European, someone who was born in Europe, basically all these inscriptions are very difficult to understand. And there's some parallel here with basically all the papers you've got to go through to understand the ideas in often in the machine learning literature. So the machine learning, not lecture, but literature may seem impenetrable in many cases, in particularly the generative modeling literature. In Bristol, we had a reading group which started nearly a year and a half ago, and it took us a while to really understand what was going on. But we felt that the topic was interesting. And what was interesting to me is that I knew that Arnaud had an interest in this. In fact, an interest that he had a long time. And I've known for a long time the quality of his work, the thoroughness of his work. And I was very hopeful and not disappointed. So that's to show you that I've known Arnaud for quite a long time. So the two people on the right-hand side are indeed both of us. I've got another picture similar. So you can play a game of trying to find the similarities between the pictures. And here you can play another game, which is to find the differences. So the picture was taken more recently. And you see I was a bit fat. That was before going up the Inaraya Inarayama shrine. Okay. So now to the slightly more serious part of the talk. So Arnaud has provided us with an illuminating overview of the developments in the area, which have occurred at a very fast pace, which I think is quite remarkable. And I won't go through all the various steps, but that's really remarkable how fast clarity has emerged. And Arnaud has played a very important role in clarifying many of the ideas and connecting some of the algorithms. I won't have time to go through all this, but that's really interesting. Just a word about basically the community we come from, the Bayesian statistics community. So I don't like the term Bayesian computation or Bayesian comp terminology, but that's the terminology that is used. And what is interesting is that in this area of generative modeling, basically people like me or Sumit or Arnaud, we knew all the tools, basically. Okay, but there are things that basically the community had missed, which was in particular the role of and the generality and aspects of random mappings, their composition and the decomposition of randomness in small elements of random things of or mappings. And that has, I think, been quite missed, whereas we all knew the things. So Arnaud had an interest in this kind of transport ideas for a long time. And I've checked that basically things were mentioned in Jeremy's thesis. And I think you mentioned 2012 earlier for your when you started working on this. So Arnaud has persevered and made sure that could work. And of course, one issue with our community is that basically we perhaps work on the wrong time scale, you know, and the slow one. Okay, so a small word about optimal transport. And basically, this is more like a mind map of the sort of things I've understood about the area. So we want to map a distribution pi naught to another distribution pi t. Why? Because there are many applications. And we do not want to choose any mapping, but we want to choose mappings that minimize a cost. And by the way, by mapping, it can be a random, this may be a random mapping. So just a question. So currently, this is limited primarily to the L2 distance. Have other distances been explored, and why? Okay, so Arnaud has taken us through basically various GM methods like denoising diffusion models. We've come with their own problems despite being massive advances in the area. And other techniques like bridge matching and flow matching have also emerged, and there are also dynamic methods in the terminology that Arnaud has used, and they got the advantage that they do not require the forward pass, which maybe take an infinite amount of time, at least in theory, on paper, in order to be correct. But in fact, they've got no guarantee in the form in which they were presented to be solving. They've got no reason to solve the OT problem or come close to solving the OT problem. So one word about the properties of the solution of the OT, and they are fundamental because these properties play an essential role in the design of the algorithm. So one thing that is important is that the solution takes this form, okay? So where you've got the reciprocal of Q, so the reference measure that you use, which turns out to be an instrumental distribution in the algorithm. Pi naught pi t just means that basically the endpoints are distributed according to the distributions you're interested in. So that's one characterization. The other characterization is in terms of a diffusion that has got this property. And that's another useful characterization. And basically, these two characterizations have been exploited in two different ways, actually in reversed order historically, in order to address numerically the problem of the OT problem. So we've got first the IPF algorithm that Arnaud has mentioned, which is an abstract algorithm, actually, but using the diffusion representation of the solution, one can approximate basically the IPF algorithm using basically diffusions and their time reversals. And there are various tricks that are quite interesting that here, in order to ensure that errors, so they accumulate, but you want to minimize the accumulation of error. What is important is to reinitialize actually each diffusion with either pi naught or pi t while alternating between the two basically optimization problems. Okay, so one issue though, which is solved in the last problem, is that basically we're learning the drift for the diffusion is required at each iteration, which can be extremely expensive, and which again is, I think, what is important in the last few slides that Arnaud presented. So IMF, on the other hand, uses the other representation of the solution. So remember, the other solution uses the instrumental distribution Q, right? And basically what you do is that you're going to exploit that. So we know that this is the solution. So we could say, that's it, we are done. But remember, we want a mapping that goes from pi naught to pi t. So that's why a natural idea is to project basically this solution onto the Markovian solution. The problem is the Markovian solution is of this form and involved this very complicated term here, the expectation, right, which you need to learn. And this leads naturally to an iterative algorithm whereby first you choose a model for this unknown quantity, and then you're going to basically alternate between using the Markovian projection and basically going back to the reciprocal of your problem, okay? And at the same time, learn the parameter theta, right? So that's the idea. So it seems that basically, in principle, we can choose Q, whichever way we want. And I have a question about this, but what is important in practice is that sampling from that conditional distribution is essential in order to be able to implement the algorithm. So I saw that there was an alternative in the last example where basically the reference measure involved a deterministic part, but I was wondering if other Qs had been exploited. So here again, the naive application of the algorithm may be a bit unstable. So, and that's a general theme in all these algorithms, in these improvements, is that basically the difficulty seems to be that one can write equations, one can implement an algorithm, but the algorithms can be quite unstable. And a big part of the game seems to be to try to stabilize the algorithm. And here again, what is important is to be able to sample from pi naught and pi t, and that's a question actually. So all these algorithms seem to require sampling from pi naught and pi t at each iteration in order to preserve stability of the algorithm. Again, this algorithm seems to, in its basic form, to require training at each iteration of your neural network that is used to model the drift. Okay, so here is my takes on the last slide, which is the basically corresponds to a paper that is not published, but Arnaud shared these slides before the presentation, so I tried to understand what was going on. And my take on this is that basically, if you think of basically the IMF algorithm, what you're trying to say is that for a given parameter theta, you've got a model, a Markovian model, which represents a distribution P. And then let's assume that you perturb your theta. And I'm not telling you in which way yet. You define another Markovian process. So you see that you're going from one path distribution to another path distribution. And basically, one way to update your theta is by basically trying to use gradient descent on an appropriate loss function, okay? And then, of course, this here is just a guess of what's going on. I'm sure there are many more details. So here is a question, actually, a key ingredient of all this consists of considering path instead of one-shot method. And basically, this type of idea is already known in the Bayesian computation community, and it's or in physics actually, it's annealing importance sampling. Okay, and I think that I had a quick peek at Sumeet's slides earlier, and I think he will give you more details about that later on. What is interesting in that setup, and there is a parallel here between the two worlds, is that in order to estimate normalizing constants in using importance sampling, it's very easy to cook up problems where the complexity is going to grow exponentially fast in the dimension of the problem, where annealing importance sampling is actually going to be, and you can prove it, at least for stylized problems, is going to be polynomial. The complexity is going to be polynomial. And it would be very interesting to know if one can establish similar results for this algorithm, because this seems to be the claim. So in conclusion, so this is a fascinating, fast-moving, and very competitive area, as one can tell from the outside, that there are numerous ideas that have been developed with standard tools, which is what I think is really interesting, is many of these the tools were around. It's just the way they've been assembled, which is really interesting. The full impact on the practice of classical statistical inference is still unclear, although Arnaud has given us a glimpse of possible uses. And finally, I would like to, again, congratulate Arnaud for his well-deserved prize. Thank you very much.
Thank you very much to the committee for inviting me to discuss Professor Doucet's memorial lecture. And I would like to also congratulate Professor Doucet on an outstanding lecture. Like Arnaud, Christophe said, Professor Doucet did send us the slides, although it was too late. I had already come to Japan and I was suffering jet lag and I was not going to change my discussion. But hearing his insights that accompany the text, because I just got the text, but to hear the extra insights that he gave today, that was invaluable. And if there is a recording of this lecture, I think I'm going to watch it more than one time again. Okay, so my discussion, hang on a second, is going to focus on sequential Monte Carlo. So this is an area, so I know Professor Doucet has worked on optimal transport since 2012, and I can vouch for that. I was at a presentation in Imperial College, and I didn't understand a word he was saying, but I felt it was very exciting. But actually, we can go back even further. We can go back even 20 years, and we can look at a piece of work that Professor Doucet had done in 2006 called sequential Monte Carlo samplers. So let me just give you the idea, and then that will lead into the discussion. So what we have here is a problem where we want to sample from a target probability distribution pi. And sequential Monte Carlo samplers is a methodology for interpolating, going from a simple probability distribution you can sample, I called it pi naught, to the one that you want to sample. So like I said, pi naught is an easily sampled distribution. And how do you, what I mean by an interpolation is the one where it's called a geometric interpolation in this case. So you basically take a fraction of pi naught and the distribution you want to sample, pi star, and that fraction is controlled by a power lambda. So if lambda is equals to 0, you're at pi naught, lambda equals to 1, you're at pi star. And if you choose a sequence of lambdas going from 0 to 1, you sample a sequence of distributions going from pi naught to pi t. Now, the available tools that one uses to solve this problem is that you have Markov chain Monte Carlo kernels that leave pi lambda invariant. Okay, so what you do is that so the basic idea of sequential Monte Carlo, from my perspective, is that if you can do MCMC, then if you can organize your computation sequentially in a more careful way, perhaps you can do much better than trying to sample pi star directly. And that's the idea of sequential Monte Carlo samplers as I like to think about it. So in this instance, you sample X naught, and how the algorithm works is then it advances the samples through the MCMC kernels that target pi 1, pi 2, until you get to the end. Then you use an important sampling correction given by this weight equation. Okay, it looks rather complicated, but it doesn't involve the kernels M. It just involves the distribution of the path of the stochastic or the interpolation. And now I would just want to give one comment about this weight before we move on to the substance of the discussion. Now you may be confused by this weight. Actually, this weight arises because now you've lifted a problem of sampling from one distribution which lives in RD to sampling from a sequence of distributions. So the problem's really been lifted to RD times t plus 1, where t plus 1 is a number of distributions in total. And this weight reflects that. It reflects, so this weight that you see in sequential Monte Carlo literature really can be expressed as the ratio of two distributions over paths, where Q is what you sampled from, and P is a specific choice that one makes for convenience, so that you have, with the only constraint being the marginal distribution at T at pi, at the end is the distribution you want to sample from. Okay, so this is SMC samplers as we knew it 20 years ago, and this is how it's being used even until today. Okay. Now, but there are some challenges. And the first challenge is really the one that you cannot escape the inefficiency of your MCMC kernel. So if your MCMC kernels are ineffective, then the distribution of XT can be very far from pi star, and embedding it within this SMC sampler framework might not give you very much. And so people have looked towards diffusions as giving us as a source of more effective kernels to sample from distributions of interest. So what about using a kernel that is only approximately pi-t invariant and not just pi-t invariant, and they come from discretizing a diffusion? And furthermore, what about tuning these kernels? Okay, so I've written the tuning parameter here as psi. Okay, it's more general than just a parameter. Now, one of the first contributions Professor Doucet has made recently using this Schrödinger bridge methods is that really he has taught us how to optimize the sampling distribution for SMC samplers when you use discretized diffusions, and he's really formulated this as this Schrödinger bridge problem. So what he has found here, you will recognize this in the formulation we've seen before, the best sampling distribution for SMC samplers should be the one that starts at pi naught, ends at pi star, and minimizes the distance between the initial distribution you chose and the one you ended up with. And I've often thought of, this not often, I've just recently thought about it because I've been following his work, following the invite to, to present a discussion, is that why a Schrödinger bridge formulation in particular? I think it's a very important connection to be made because there is a practical solution to this problem, and it's called dynamic programming. And there's a lot of work on implementing dynamic programming in a computationally feasible way. So there's a nice connection with the literature on optimal control. Okay, and this is a reference for that work. And the other challenge I want to talk about, which I feel Professor Doucet's work has solved, is this business about selecting the weight for the SMC samplers so that it targets the right distribution. So this weight that people have been using, and I've used myself, is one that is there for convenience, and because it only uses a sequence of distributions you want to sample from. Okay. But it has a lot of inefficiencies because this weight can suffer a lot of variance, or more mathematically, the chi-square distribution between the path measures, because you're really trying to substitute a sample from Q as a sample from P, can be very big. Okay, and that's the penalty we pay. And so the inefficiency of the weight has also been solved, but this time with a Schrödinger half-bridge problem, where Professor Doucet has formulated in this paper here in 2022, where he says that the best weight you can have is the one that approximates the reversal of Q star. And because you have to compute this, he has computed this reversal using a neural network approximation and using a score matching criteria. And the work and the numerical results in that paper seem to indicate that this makes a very, very big difference. So really the substance of the discussion now can be described in this few lines. So firstly, I would like to congratulate Professor Doucet by saying that there's 20 years of thinking behind annealed importance sampling, which is the predecessor of sequential Monte Carlo samplers. And remarkably, all this thinking there's a clear line of thought through it until today. Okay, there are clear connections being made today with what has gone on in the past and improvements of that past. And it's generally a new methodology for generalizing and optimizing SMC samplers. And I think that's one very exciting aspect of what Professor Doucet has been working on. So I've got really two questions, not as many as Christophe had. I lost count after a while. So I would say really, look, so from a person who's not interested in machine learning and just interested in statistics, what challenges remain in developing SMC samplers, or these challenges or these accomplishments that I've talked about, are they really the end here? Or is there a lot more to be done? And what I would like to see is, and this again links to what Christophe said at the start, there have been a lot of false promises in machine learning, perhaps. Not intentionally, but maybe the inexperienced reader feels that way, that they've read something that hasn't turned out to be as effective as they would like it to have been. But what I would like to know is that with these advances applied to SMC samplers, do we expect to see spectacular gains, like Professor Doucet has talked about at the start of his lecture, in generative modeling? So These are my two questions, and I would like to congratulate Professor Doucet on his accomplishments and the memorial lecture award.
For Christophe, yeah, the thing about the cost, it's actually important because when you look at the Schrödinger bridge, on essentially, you see, why do we have the quadratic costs when I have the Brownian motion? Because basically this is minus log the transition of x1 given x naught under the Brownian motion. And in a sense, obviously it's true for any reference process. And this is not necessarily, obviously, you know, if you give me an arbitrary cost, I'm not going to be able to identify a reference process that satisfies that. So it's true this is limiting in this respect, for sure. Second thing, indeed, if Q is the reference process is a complicated process, the reciprocal projection, which was trivial in my algorithm, because it was just like you have sample from your coupling, and then you just draw a Brownian bridge, become complicated, because now we need to be able to sample from the bridge of the reciprocal process. It's feasible, like people have done that, but obviously you need to make a new approximation if the reference process is complicated. So that's not trivial. I think the kind of main limitation which holds even if you have a Brownian motion as a reference process in all this algorithm is the fact that essentially after we do a Markovian projection, we need to obtain new sample from the resulting coupling. And that does involve actually solving numerically the SD. And that is much more complicated than for diffusion process. Because for diffusion process, basically, you have a forward diffusion, which is typically Arndt-Beck, or you use some kind of stochastic interpolant, and you don't have to run the diffusion forward directly. You can just sample at any time, any intermediate state in basically one line. And this is very important when you do the training, because it makes the training much more efficient than if you have to unroll the whole diffusion so as to basically simulate the state xt. So these are limitations, and this is what people call, this is the discussion at the end between what they call simulation-free on algorithms which are not simulation-free. And I say the problem is like simulation-free algorithm that bypass that by trying to solve the Singh chord algorithm and then trying to draw a bridge, turns out not appear to scale in terms of number of samples for the application we have. Also, about a question about complexity reduction, whether essentially having this kind of diffusion idea really kind of breaks some barrier. I agree. We haven't been able to formalize really this idea that the iterative refinement seems to be bringing something to the table. And I agree, this is something that is worth exploring. I do believe it's the case, but we have no result whatsoever. And actually, I don't quite know how to formulate the problem. It's more complicated. It's not like I even know how to formulate the problem. I'm actually quite unclear about that. I'll get back to the impact on statistics because at the end, because Sumeet asked a similar question as well. So about a challenge in developing SMC sampler, whether those ideas are useful. So, I mean, you quoted the paper we have from with Benton, where we had this idea to do the approximate dynamic programming. I mean, at the end of the day, we never submitted the paper because we are not happy with the result. And I think the method was too limited. It's not flexible enough. Somehow we wanted to have some kind of simple approximate programming. And essentially it turned out that he was just not flexible enough for the problem we wanted to solve. It's the same thing when you do control SMC and you just make some kind of quadratic approximation of the value function. This is the same problem. It's not really flexible enough, I think, to address really challenging problems. So in the model, problems we presented, it was kind of working fine, but it's not, I don't expect this kind of things to work well for complicated target distribution. And that's why we decided never to submit the paper. On the second thing, where we use core matching to to kind of learn the optimal reversal. I would say that was more a paper for me about finishing business than a particularly useful thing. I think it's an interesting. I think in most situations, particularly if you were to run a homogeneous Markov chain, then, but it's not, it's useful in a scenario where you can do this kind of amortized variational inference. So this is where the kind of application we have, where there you can really amortize the cost of the learning the time reversal, and then you can expect gains. In a general case for statistical problem, I don't think it's useful, really. Yeah, as a question, final question, what will be the impact of these techniques for all this kind of, I'm not going to say Bayesian computation, but Bayesian statistics? It's unclear. I think for me, there are some ideas that can be out there, but there's a lot of problems. For all the standard classical, sampling problem we've been working on for many years, I think those methods, it's quite unclear yet whether they're bringing anything to the table. I'm really, really not convinced yet that there's still ideas missing. So I've seen some promising results, on actually using denoising diffusion for general Monte Carlo sampling, but the scope remain extremely limited. So I'm not, I think there's interesting idea for the community to build on, but for sure we haven't yet really, really solved this problem. This sampling is a much more difficult problem than generative modeling. It's not even remotely comparable. It's like orders of magnitude more complicated because somehow generative modeling is kind of interpolating, between sample, a kind of clever way on this, some kind of magic, neural net inductive bias that appear to be extremely useful, but sampling is much harder. You have to know where the action takes place to sample. It's orders of magnitude, I think, in my opinion, more complicated problem. So yet I'm quite hopeful. I really want to spend more time working on this type of sampling application. Hopefully, being able to make progress on the more traditional problem I've been looking at, but yeah, still a lot of work. So I'm not quite clear what will be the future. Perhaps for more the simulation-free, the kind of alternative to ABC in high dimension, this is where so far I think is the most promising. But yeah. So, thank you.
Professor Kamatani, he is the organizer of this session. Is there any comments or question?
From me, just a short comment. So what is known theoretically for your work? Convergence.
So what we have
so far?
What we have for for DSBM, we have the convergence when there's no approximation method, which is obviously a big assumption because obviously in practice you have this Markovian projection. You cannot implement it exactly. You need to make some approximation. You learn some kind of flow matching or some rich matching type objective to minimize. So this is where there's a gap in theory. So there's been work actually by a group of people trying to study the robustness of this kind of Schrödinger bridge, approximation. I think it was for the previous work we had done for like this IPF type work. But they had some result where they were actually proving some kind of stability result or some bond. So that does exist. I'm aware of one paper that does that actually. And it's by people by Morgan Stanley, which is a bit a bit surprising, but it turned out they have a team working on this type of problems there.
Thank you.
Okay. Any comments? Okay.
Thank you for great and stimulating talk. I have a question about the formulation of the Schrödinger bridge. So you formulate the Schrödinger bridge as a minimizer of the callback divergence to the Brownian motion, and
actually it's more general, but obviously all
Okay.
the presentation is for the Brownian motion, and as I explained, numerically the fact it's Brownian motion makes the implementation much simpler.
Okay, I see. My question is, in the case of optimal transport, we have a freedom of choosing the cost function, for
Yes.
example. Is there any similar extension of the Schrödinger bridge to more
No, that I know, actually. So as I was telling, actually, Christophe, you end up that in our case, when you try to do the equivalent of, oh, I go from dynamic to static, you would end up that literally the Schrödinger bridge is solve the static problem, the static transport problem that corresponds to minus log of the transition probability of x0 given x0 under the reference process. People, there's been after that like some generalized version, like I think Ricky Chen did this kind of things, but it is not what you had in mind for general cost, actually. And that's actually a limitation. So it turned out for a lot of the generative modeling application we are looking at, L2 is okay. Or, you know, we work in latent space, and then we have L2, and it's actually a sensible metric. But I do agree this is a severe limitation, yeah.
Okay, thank you.
Thank you. Time is almost over. So thank you for joining us for the fifth Akaike Memorial Lecture. It has been a great honor to host such an amazing lecture. I would like to thank Professor Doucet and our two discussants, Professor Andrieu and Professor Singh. In closing, I would like to thank those who helped prepare for this event, and thank you for joining us today. Have a great day.